Greetings, pre-calculus students, to another day, another lesson in our unit on sequences. In our previous lesson, we looked at a couple of different problems in relation to arithmetic sequences, as well as an intro to what a factorial is. In today's lesson, we will discuss another type of sequence. So we've looked at arithmetic sequences. Today we're going to learn about something called geometric sequences. But before that, I'm going to quickly go over the solutions to the bell ringer if they were not covered in class. So if they were not covered in class, I will quickly go over them. If they were covered in class, then you can just skip over this. Okay, so given the fifth term of an arithmetic sequence is 17, and the 10th term is 52, find an explicit formula for the nth term of the sequence. So let's see, according to this means that 17 plus 5d is equal to 52. So we're going to solve this for d, so minus 17, so 5d is equal to 35. Divide both sides by 5, and d is equal to 7. So that means the common difference is 7, which means our explicit formula, which if you recall is a sub n is equal to dn plus c. That's what an explicit formula, the standard form of an explicit formula for an arithmetic sequence looks like. We know the d value is 7, so 7n plus c. Now we just have to figure out the c value. Well, one way in which we can do that is we can use one of these terms. So let's use one of these terms to figure out what the c value is equal to. Well, if a sub 5 is equal to 17, that means 17 must be equal to 7 times 5, because that is what n is equal to. N is equal to 5 for a sub 5, plus c. So we have 17 is equal to 35 plus c, which means if we subtract 35 from both sides, c is equal to negative 18. So c is equal to negative 18. So that means our explicit formula for this arithmetic sequence is 7n minus 18. That is what you should have gotten. We can easily test it out. If we plug in 10, do we get 52? We do get 52. So that means we did it correctly. All right, so let's get to today's lesson now. So once again, in today's lesson, we will talk about this idea of geometric sequences. So we've seen how arithmetic sequences are sequences where the difference between each consecutive term is the same, right? There's a common difference. Well, now let's look at what geometric sequences are. So before that, just a quick recap. This is what we talked about in our previous lesson. An exclamation mark or n factorial is defined as the product of all positive integers up to n. So for example, we saw that 5 factorial would be equal to 1 times 2 times 3 times 4 times 5. That is what 5 factorial would be equal to. So that is factorial notation. All right, let's get to our new type of sequence, geometric sequence. So example 1, find an explicit and recursive formula for the following sequence: 6, 12, 24, 48. All right, so if we look at this, for some of you, it might be obvious what the pattern is. For some, it might not be, but it looks like the pattern is we're just multiplying by 2 every single time. No, because to go from 6 to 12, we multiply by 2. To go from 12 to 24, we multiply by 2. To go from 24 to 48, we multiply by 2. So it looks like the pattern is multiply previous term by 2. All right. So we can easily write a recursive formula for this at least, right? We can easily write a recursive formula for this. So the first term is 6, a sub 1 is equal to 6, and then a sub 1 is equal to a sub 1 minus 1, because that's the previous term, times 2. So that's a recursive formula. All right, so that was pretty simple, because once again, since we're just taking the previous term, multiplying it by 2, that means our recursive formula is just a sub n minus 1 times 2. And as I've reminded you all before, don't forget, for a recursive formula, you have to specify what that first term is. You have to specify what that first term is. All right, let's talk about the explicit now, which might not be obvious. Well, we just said that we're just multiplying by 2, right? Multiply by 2, multiply by 2, multiplication by 2. So in other words, it's just repeated multiplication. So now we have to think back to all the different math concepts we know. What is repeated multiplication another word for? Repeated multiplication, when we repeatedly multiply by something. What's another way to write that? The answer? Exponents. Exponents are repeated multiplication, right? 2 squared is 2 times 2. 2 cubed is 2 times 2 times 2. So if you want to repeatedly multiply by something, you use exponents. Okay, so we know this is related to exponents, all right? So since we're repeatedly multiplying by 2, I guess that means that the base of our formula is going to be 2 to the n power, right? Because that's the number that we want to repeatedly multiply by 2. Well, does this work? Well, let's see. If the first term is 6, if I plug in 1, I get 2. So that doesn't work, all right? Because remember, we want the first term to be 6, but if I plug in 1 into this formula, I don't get 6. I get 2, because 2 to the first power is 2. So we got to figure out, how do we determine what goes out in front? Well, if I plug in 1, I get 2, but I want 6. Well, I could change that 2 to a 6 by just multiplying, right? I could just do this. That turns it into a 6, because 3 times 2 is 6. Well, it works for the first term. Does it work for the second term? Well, let's see. If I plug in 2 into this formula, I get 2 squared. 2 squared is 4. 4 times 3, hey now, it is 12. So it works for the second term. Does it work for the third term? If I plug in 3 now for the third term, I get 2 cubed. 2 cubed is 2 times 2 times 2, which is 8. 8 times 3 is 24. Looks like it works. And then you can easily test it for the fourth term as well, and you would see it works. So the explicit formula for this sequence is 3 times 2 to the n power. Once again, it's 2 to the n, so it's 2 with an exponent because we want repeated multiplication, because we're just repeatedly multiplying by 2 for every term, for every next term. And then we had to also put in this 3 times part because we wanted our first term to be 6, right? And if we wanted our first term to be 6, we wanted to do 3 times 2, which gave us that 6. So let's see what kind of conclusions we can make from here. So generalization. So once again, our sequence was 6, 12, 24, 48. And our explicit formula was a sub n is equal to 3 times 2 to the n power. Well, we already talked about that this 2 comes from the fact that we're multiplying by 2 repeatedly. Right? We're multiplying by 2 repeatedly. So that's why the 2 has the exponent. We're not multiplying by 3 repeatedly, right? Because once again, 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48, so on and so forth. So we're always multiplying by 2. All right, well, where does the 3 come from? Well, the 3 is actually, it comes from kind of the same place where, if you recall, when we did arithmetic sequences, the C value came from. The 3 is your 0 term. Or in other words, what happens if we went backwards, right? So we know 6 is our first term. Well, what about if we wanted to know the number before 6? Well, instead of multiplying by 2, we would do the reverse, which is division by 2. So the 0 term, quote unquote, would be 3, right? If you went backwards, if instead of going forwards and multiplying by 2, you went backwards and divided by 2, you would get 3 as your 0 term. So that is where that 3 comes from, okay? So let's generalize this a little bit. So first, some definitions. A geometric sequence. A sequence whose consecutive terms have a common, not difference this time, a common ratio is called a geometric sequence. In other words, if the ratio between consecutive terms is the same, then it can be concluded that the sequence is geometric. So this time around, we're not looking for the difference between each term. We're looking for the ratio between each term. And that's something we'll talk about in our next example, so don't worry. That's something we'll get into deeper in our next example. Or the example after that. I forget which one. So that's the definition of a geometric sequence. It has a common ratio between consecutive terms, common ratio. So not common difference this time. So we're not adding or subtracting the same number for each iteration. We're multiplying or dividing by the same number for each iteration. So that's where we end up with that common ratio. So the nth term of a geometric sequence, the nth term of a geometric sequence. Oh, wait a second here. Change this up here. There we go. Some corrections were needed. So the nth term of a geometric sequence has the following form. A sub n is equal to a sub 0, so the 0 term, right, the term before the first term, times r. So r is the common ratio. R is what we call the common ratio, or in other words, just think about it as what number are we multiplying repeatedly. In the example that we did, the number that we were multiplying repeatedly was 2. So that's why the r value was 2. And then to the n power, because once again, we want that exponent because we want to multiply repeatedly by that number. Okay, so let me write it more nicely here. So a sub n is equal to a sub 0 times r to the n power. That's your nth term of a geometric sequence. All right, let's use this formula. So example 2. Write the first 5 terms of the geometric sequence whose first term is 3 and whose common ratio is 2. All right, so they tell us that our first term is 3 and our common ratio is 2. So in other words, once again, that is the number that we're multiplying repeatedly. Multiply by 2 repeatedly. All right, so that means if our first term is 3 and our common ratio is 2, that means our next term is 6. And then we keep on going from there, right, if we wanted to. So 3, 6, 12, says first 5 terms, 24, 48. That would be the first 5 terms of a geometric sequence whose first term is 3 and whose common ratio is 2. Okay? Now, let's talk a little bit about this common ratio. Like, how do we know it is 2, or why do we call it a common ratio? Well, previously when we worked with arithmetic sequences, I showed you that to find the common difference, you literally just took any 2 terms, consecutive terms, so 2 terms right next to each other, and you subtracted one from the other. And then it told you the common difference. Well, we can do the same thing with geometric sequences as well. We take any consecutive terms. So let's say, for example, I took 12 and 24, and you divide the 2 terms. So divide the 24 divided by 12, and that gives you 2. Or if I wanted to choose like 24 and 48, I could do 48 divided by 24 and get 2 again. So that's why it's called a common ratio, because you literally take the ratio between consecutive terms and calculate them. And as you can see, it is always going to be 2. If I chose 3 and 6, I would get 2 again. If I chose 6 and 12, I would get 2 again, so on and so forth. Now, the key here is you got to make sure you take the later term first, right? So we're always doing 6 divided by 3, or 12 divided by 6, or 24 divided by 12. Don't do 3 divided by 6, because remember, we're going forwards. We're not going backwards. Okay, we're going forwards, we're not going backwards. So you always want to choose the more later term first, okay? So the second term divided by the first term, or the third term divided by the second term. Not the other way around, not the first term divided by the second term. All right, so just be careful there. All right, let's look at one more example here. So example 3, find a formula for the nth term of the following geometric sequence. Okay, so this time they just give us the sequence of numbers, okay? They give us the sequence of numbers. Oh wait, were we supposed to find a... whose first term, right? Oh no, okay, for a second there. So 5, 15, 45. So once again, the explicit formula, I should have specified here, find an explicit formula, okay, is going to be a sub n is equal to a sub 0 times r to the n power, okay? So a sub 0. Well, let's find out what the common ratio is first. Now, some of you might be able to look at this sequence of numbers and know right away, oh, it's just multiplying by 3 every single time. Okay? But if that's something you don't see right away, or if that's something that's not clear to you, then once again, remember, we can just take the ratio of consecutive terms to determine it. So let's see if we did 5 and 15. So 15 divided by 5. Ooh, that's 3. Okay, that's a start. Let's do 15 and 45. 45 divided by 15 is equal to 3. So it looks like the common ratio, or the number that we're multiplying by repeatedly, is 3. All right? So common ratio is equal to 3. So we have a sub n is equal to a sub 0 times 3 to the n power. So once again, 3 has the exponent because that is the number that we are multiplying repeatedly by. Okay, that is the common ratio between consecutive terms. Now let's find that a sub 0. Let's find that a sub 0. So remember, a sub 0 would be the term before the first term. Well, let's see. My first term is 5. I want to figure out what the term before that would be. Well, if I'm going backwards, that means instead of multiplying by 3, I'm dividing by 3. Well, what's 5 divided by 3? Well, that's going to be a decimal. And typically, I personally like to avoid decimals, so I'm just going to literally write it as 5 divided by 3. All right? Because we can't really simplify that unless we wanted to write it as 1.6 repeating. So we're just going to leave it as 5/3. So that means the zero term is 5/3, which means our explicit formula is now equal to a sub n is equal to 5/3, because that was our zero term, or a sub 0, times 3 to the n power. So let's see, does that work? Well, let's test it out. The first term is 5. So let's plug in 1. So 3 to the first power is 3 times 5/3. So let's see, that's 15 over 3. 15 over 3 is 5, so that works. What about the second term? Second term is 15, so let's plug in 2. 3 squared is 9, because 3 times 3 is 9. So let's see, 9 times 5/3 is 45 over 3. 45 over 3 is 15, so that works. All right, let me quickly show you what I'm doing. So test. So for example, we said the second term is equal to 15. So if we test it out, a sub 2 is equal to 5/3 times 3 squared. Well, 3 squared is 9. So 5/3 times 9 gives us 45 over 3. So 45 divided by 3 is 15. So it does work. It does work. And sometimes it's a good idea to check just to make sure we didn't do anything wrong with our formula. But that is the explicit formula for the nth term of this geometric sequence. Okay? So that's it. Just a little intro into what geometric sequences are, as well as how you find the explicit formula for them. And then find the 9th term of the sequence. So let's do that. So let's see, a sub 9 would be 5/3 times 3 to the 9th power. Let's see, what is 3 to the 9th power? I got to get out my calculator now. 3 to the 9th power. All right, give me a second here. So 3 to the 9th power. Okay, it's a big number. It's 19,683. So now let's multiply that by 5/3, so it's times 5. So that's 98,415 divided by 3. Let's divide that by 3. So we get 32,805. So that would be the 9th term. The 9th term would be 32,805. So for some of these, the numbers will get quite large, because when you're multiplying, right, those numbers are getting large pretty quickly if you keep on multiplying again and again and again. Okay, so that was it for this lesson. The rest will be on your own problems. So here's your first set. Okay, so find the explicit formula for the sequence. So find the explicit formula and then find the indicated term. So for part A, you find the explicit formula, find the 9th term after that. Part B, find the explicit formula, find the 7th term after that. And then part C and D, the same thing. Okay, so this is basically just more a chance to do example 3, a problem like example 3 on your own. Okay, so that is it for today's lesson. I hope it went well. If there are any questions, obviously, as usual, please reach out to me to whatever channels you feel most comfortable with. Otherwise, I hope you guys stay safe, and I hope you enjoy the rest of your days.